So it looks like everyone is been admitted. So welcome to our fourth week of the Catalysis webinar. It's really an honor to introduce today's speaker, Dr. Frund from the Fritz Haber Institute. As an introduction to this webinar, I'm Lorianne Schultz, and we also have on here Katie Slavinska. We're from the American Vacuum Society at the University of Central Florida. The way that this webinar is organized is Dr. Frund will give a 30 to 45-minute talk, and at the end of that, we'll have a 10-minute question and answer period. So at any time during the talk, if you have a question, please don't try to mute yourself or anything like that. Please just go ahead and type it into the chat box, and I'll read those questions out loud at the end of the talk, at least as many as we have time for. So as I said, I'm super excited and honored to present today's speaker, Dr. Frund. He earned his BS in chemistry and physics from the University of Cologne, Germany in 1972, and went on to pursue his PhD in chemistry under the guidance of Dr. Georg Hollnicker. He obtained his PhD in 1978 and then took a postdoctoral position at the University of Pennsylvania and Xerox Corporation Webster. He went on to work as an assistant professor at the University of Cologne and then associate professor at the University of Erlangen-Nuremberg for 4 years and a professor at Ruhr University Bochum for 9 years, and then became the director and scientific member of the chemical physics department at the Fritz Haber Institute in 1996. He retired last year after 23 years, although he's not really retired, and he has been honored with the title of Emeritus Professor. And in addition to holding guest professorships at universities around the world, including Northwestern, Massachusetts Institute of Technology, the University of Technology and Science in China, and the Institute of Catalysis in Japan, Dr. Frund has been honored with the title of fellow or honorary member in chemical societies around the world, including Germany, America, Japan, and China. Dr. Frund has been honored with an extensive list of awards and honors, only several of which are the Centenary Award and Lecturer of the Royal Chemistry Society, the Gabor Sommerjee Award of the American Chemical Society, the Carl Ziegler Award for the German Chemical Society, the Blaise Pascal Award in Material Science, the Award for Service from the European Chemical Society, the Langmuir Award from the American Vacuum Society, and the Boda Award, as well as the ACS Award for Surface Chemistry. And that's only a few of them. So we're very honored to have you today, Dr. Frund, if you'd like to go ahead whenever you're ready and present.
Well, thank you very much, Lorraine. It's a great pleasure to be here, and thank you very much for initiating my talk. I hope you can now see the transparencies.
Yes.
I would like to speak about experimental modeling of catalyst materials at the atomic scale. I will briefly introduce you to the subject, and then I have chosen two topics that could be of interest. One is connected with the identification of active sites at the oxide metal interface. And the second one is actually a topic that I never thought surface science can actually contribute to, and that's reactions in confined space, which is an important aspect, for example, when you work with zeolites. Now, just as an introduction, we all know what catalysis is, a kinetic phenomenon. It doesn't change the thermodynamics, but it does change the way the reaction happens. That is, the activation energies of the materials that go into the reaction, as is indicated here schematically. So we might have, or we often have, without a catalyst, a very large activation energy, which is then modified through the catalyst and makes things easier. We do differentiate between various ways of doing a catalysis, and there is the heterogeneous catalysis, where you have two phases in contact, often a solid and a gas phase or a liquid phase. We have the homogeneous catalysis, which happens, for example, at organometallic complexes in solution. that is, the catalyst and the reactive material is in the same phase. And then we also differentiate enzymatic catalysis, which is sort of in between, because the proteins that form the enzyme have some resemblance to a solid, but it's really a homogeneous way things happen because it happens in one phase. So this is, in a way, an artificial dividing it up, but that's the way it is typically handled. The way we do our, we perform our investigations is based on ideas that very early on put into science, basically through the development of surface science, as pushed forward by Gabor Sommerjai at Berkeley and Gerhard Attel here in Germany, for example. And in 2007, Gerhard Attel actually got the Nobel Prize for identifying the way how a nitrogen molecule is activated on an iron 111 surface, that by absorbing the nitrogen on the iron surface in specific sites, the activation energy, which in the gas phase is huge, is reduced very much. The nitrogen splits. This triple bond, this very strong bond, is split, and then once the molecule is split, the nitrogen atoms are hydrogenated, and eventually ammonia desorbs from the surface. And this is done on a single crystal. So we use these single crystals in a sort of artificial environment in ultra high vacuum to investigate these steps. And a very important way forward nowadays is to put all this into reactive medium as in real conditions, and that's what people call operando spectroscopy. But I will today focus on systems that are sort of in line with this procedure that I just outlined. The way we try to, what we try to do is indicated here in this figure. We are on the left-hand side, you have the most simple system, which is almost a molecular system. You can have a cluster with an active in the gas phase with an active site, and you can identify that by gas phase techniques. The next step would be to go to single crystal metal surfaces, as was done by Gerhard Attel, for example, and identify the surface structure of these metal surfaces. But we know that real catalytic materials are more complex. They are, oftentimes, they are consisting of metal particles that sit on a support. So we need to be able to include those degrees of complexity. And so we need to study not just single crystal metal surfaces, but we need to study support materials such as oxides, which are insulators, and that has a consequence I will come to later. And then you can put these small metal particles onto these oxide, and then people would argue in the early days that the structure of these small metal particles resembles single crystals. That's true, but if the size of these materials become finite, then the electronic structure of it changes in comparison to a single crystal. And also the interaction with the substrate alters the chemistry of the system dramatically, which can even lead to the fact that, and that's shown on the right-hand side, that the supporting oxide migrates onto the metal particles and encloses it. It's a phenomenon that in catalysis is called a strong metal support interaction. So by including these degrees of complexity, we are eventually hoping to approach the system that is really the one that is active in a catalytic system, and we can identify the various steps directly. One important aspect that is also indicated here by these green and red bars below is the interaction between experiments and theorists. Theory for the simple system can directly compare things to experiment. The more complex the system becomes, theory at the moment still lags behind, but it's pretty sure that in the near future, we'll have the situation here that theory is basically in line with what experiments can do, and we can do direct comparison, and that's often very, very helpful. Now, our specific approach takes into account the fact that oxides, which are support materials, are often insulators. And insulators, when you use the toolbox of surface science, have a problem because we often use charged information carriers. And if you use charged information carriers, there's the problem of charging. By growing oxides in thin films, you can avoid that. If you grow them on a metal, on a conducting metal substrate. Of course, you have to make sure that the oxide film is thick enough that it resembles the bulk material, because if you grow it in very thin sheets, as shown in this slide here, then you maybe have an interaction of this oxide metal interface with what happens on the surface. While when you grow the film thick enough, you can avoid that. And so you can, to some extent, control this, and that's actually quite important. I will not dwell on all the cases that are shown here. I will briefly mention that you can modify once you have grown the film by putting dopants in. But in the end, I will show you a system where we grow a very thin oxide film that actually can be removed from the metal because it's only bound by dispersive forces to the metal. And that opens up a space in between the oxide and the metal that then finally allows you to study systems that resemble confined space situations. So much for an introduction. In general terms, this slide is meant to show that when you prepare these thin films, you can actually characterize them at the atomic level very well. For example, you see an STM image of magnesium oxide below, and of course there is no chemical identification of which is magnesium and oxygen, but if you create a defect in the system, here, for example, you can see that the arrangement of protrusions is the same, but you see a different darkness. And that is because you have removed an oxygen atom, which then tells you immediately what you are imaging is actually the magnesium atoms and not the oxygen atoms. And you can control that to some extent by changing voltages and so forth. You can then also apply photoelectron spectroscopy and see chemical shifts in great detail, and we will not go into the details of this, but that is something that is very useful and where the thin film approach helps a lot. Now let's come to the first set of studies on at the active site at the metal oxide interface. Now, the problem that you have to recognize is if you want to study the oxide metal interface, for example, by using scanning tunneling microscopy, is that, and that's depicted in the upper part of the figure, schematically, you see this, the blue thin film sitting on a darker metal substrate and these golden particles on top. The tip, of course, is compared to the size of the particle, huge. So if you have a three-dimensional particle, various parts of the tip will interact with the particle simultaneously, and that destroys the atomic resolution. You see an image, or you see a real example here on the left-hand side, where this is a palladium particle on an aluminum oxide thin film, and you can see beautifully that the flat top of that particle is atomically resolved. Even if you enlarge it a little bit, you can clearly see it. But when it comes to the interface to the oxide, you can see that things get more less well-defined. You can see maybe the first 2-3 layers below the top layer, but when it comes to that interface, it's difficult. However, if you can prepare metal particles that are flat, that basically have only one layer, then this problem doesn't occur, and you can really get to the edge. And that was one of the approaches we started to use, and you will see once we've gone through it what the whole story means. One important point is, again, as I said before, the interaction with theory. In a paper where Uzi Landman and Gianfranco Pacchioni calculated the electronic structure of gold-20, which actually has this tetrahedral shape, as Liexing Wang has actually, Brown, I think, has actually shown experimentally, that gold particle, if you put that on a bulk oxide, stays three-dimensionally, basically doesn't change morphology. And that is not unusual because a metal does not usually wet an oxide, it balls up on an oxide. However, if you go to a thin film situation, like here, the most stable situation, and that's where theory comes in, is no longer the bulk, but it's actually this flat pancake-like situation. The reason for this is that the gold, which is one of the most electronegative metals in the periodic table, it's also almost as electronegative as iodine, wants to attract electrons. And giving the chance to attract electrons through the presence of the metal support then stabilizes, to some extent, this interesting pancake structure. And that was a prediction. And so is it really true? And one of my postdocs, Martin Sterrer, who is now a professor in Graz, has done the study. And you see here the example. This is magnesium oxide, 3 layers, which are thin, 8 layers, which are already representing the bulk situation. And it will take me too long to explain to you in detail why 8 is thick and 3 is very thin, because it sounds as if there is no big difference. But the fact of the matter is that when you look at the shape of the particles on the 3-layer film, it's always 2-dimensional, while on the 8 layers, it's 3-dimensional. And that, of course, means that also the charge transfer from the substrate is different, because the charge transfer triggers the 2-dimensionality, and the 3-dimensionality has much less, if any, charge transfer. So that is something to keep in mind, because it has consequences. Another thing is, if you have electron transfer, if you really want to know what's going on, you need to be able to count electrons. Counting electrons is not so easy. However, if you have small particles like these pancakes, then you can look at the SDM, at these particles, and you see that they have interesting shapes. They have these flower patterns, and you can do this for the occupied states of the system and the unoccupied states of the system. This is actually a gold 18 cluster. And the structure of these things, they can be explained. And the explanation is given in the next slide, and was proposed by Hannu Häkkinen from Finland, from Helsinki, from Jyväskylä. And it's like in a simple linear chain quantum mechanical model. You remember that in the ground state, there is a wave function that has no node. A second one up has 1 node, and so forth. And in the case here, the 1s state is the ground state. It has no node, P has 1 node, D has 2 nodes, F has 3 nodes, and G has 4 nodes. And if you now go back and look at the number of nodes in these things for the occupied part and the unoccupied part, you can see the highest state that is occupied has 4 nodes, and so has the first unoccupied state, which means that you have a G orbital. And now you can just put the electrons in and count how many electrons do you need to put in to have that G orbital filled. And the outcome is that this is a gold 18 4- system. And that's, of course, allows you to count the number of electrons, and the number of electrons transferred is pretty big. Now, if you go to a more realistic, not so symmetric particle, then the situation changes a little bit, because you cannot really look at the nodal structure so much, because the symmetry is no longer given. And then you can still see that there are interesting features. And this is an island of gold, a flat island of gold. These are individual gold atoms, because we deposit the gold, I forgot to say that, by vapor deposition from the gas phase. Now, all right. This is, interestingly, these bigger protrusions are located at the rim of the particle. And because it's at the rim, when we look at these conductance images, you can actually see the protrusions at the rim. And we are still in the process of understanding each one of the protrusions, because Hanno Häkken's theoretical prediction is that the protrusions are mainly localized at the kinks of these clusters. And that's a very interesting aspect that you can investigate with inelastic tunneling spectroscopy. It's something we're doing at the moment in the framework of a European Research Council project. Now, the point is, if you have these particles, you want to interact them with molecules. And of course, as a surface scientist, you typically use CO. Turns out, I don't want to go through the story in detail, that CO is too mobile, even at low temperatures. And that's why we have gone to use isoferrone. That's a 6-membered carbon ring with a CO hanging off the ring, so to speak, a carboxyl group. And it has this, space-filling shape. The interesting thing is that Christian Stieler, who was the PhD student, now working for Siemens, who did this, was a physicist, and he said, oh, look at this thing. I don't know what isoferrone is, he said, but this looks like a CO molecule, so I can understand this. Anyway, he showed with infrared that it indeed is isoferrone. You can see the electronic spectra of that state, and you can see individual molecules sitting on the rim. The nice thing about SDM is SDM cannot only measure electronic or vibrational states, but it can also measure, it can also be used as a tool to handle systems, to change them. So you can actually modify it by putting the tip on these molecules. They're only relatively weakly bound, and you can take them away from the rim. That creates a particle, this particle, which is the one with the molecules and without. So you can directly compare on one system the naked particle and the molecule covered particle. And these effects on the isoferrone can be understood within a simple picture that you know from the particle in a box. It's shown in the middle to start with. This is what I said before: ground state, no node, one node, two nodes in this case, and of course the width of that box determines the energy spacing of the states of the system. So if you, for example, widen it, as is shown on the left-hand side, they narrow. The energy differences get smaller. And in the case of the isoferrone, in fact, the molecule interacts very weakly. So it gives the wave function of the gold particles, in this case, the opportunity to tunnel out further, which sort of effectively widens the box, and that leads then to this change in the slope here as shown. However, if you find a molecule that actually pulls electrons out of the gold, localize them at the rim, then the electrons in the gold system will be pushed away and confined in a smaller space. That is, the box gets smaller, and the energy distance between the states widens up, and that's shown here, which is reversed to the case before. Now, whoops. So the question is then, what is this molecule that leads to this squeezing of the gold atoms? And the answer is, it's carbon dioxide. And what I'm going to tell you in the next 5 minutes or so is what I show you here. And that's, we have the situation, silver is the substrate, magnesium oxide is on top. We can grow the two-dimensional particles because of the electron transfer, and there is a way to change temperatures so that you can get away with three-dimensional particles interacting with the system as well, as shown on the left. Now, CO2 is known to be thermodynamically extremely stable. However, only then when electrons are not around. And that was shown many years ago in the molecular beam studies. I'll give you here some references. If you take a CO2 and you put an electron onto it, it costs you about 0.6 eV. It's actually shown on the slide on the right-hand side. if you even take a CO2 dimer or higher polymers, aggregates, clusters of the CO2, you actually gain energy by putting electrons onto them. You can see that you get almost 1 eV if you take a CO2 dimer and put an electron onto it. That was shown many years ago. And so CO2 can be activated. And what happens if you have a CO2 minus, a CO2 dimer minus? If it takes another electron, what do you get? You get a very interesting and very reactive molecule. It's oxalate, C2O4 2-. And that's actually what happens. And I'll show you in a minute. This is the slopes that you saw before. And up there you see SDM images of the gold particle and the oxalate molecules sitting around. How do we know it's oxalate? Well, we do infrared spectroscopy. I will not go to the details of interpreting the spectra. The point is the left-hand side is the gold free, and you already see CO2 is activated. It forms actually a CO2 minus directly, because at the oxygen defects that you always have in these layers, the CO2 can pick up 1 electron and stabilize a carboxylate on the surface. And you see that there is always isotopic labels involved in order to identify the formation of chemical bonds. And the very beautiful thing about the thin film technique is not only can you vary the isotopic labeling in the molecule that you absorb, but you can also change the isotopic label in the substrate, because you can grow your magnesium oxide film with oxygen of a different isotope. And so you can then see whether the oxygen of the substrate is involved in the chemistry that you observe. And that's what you see on the right-hand side. You see this middle peak, which is still this carboxylate on the defects, but the 2 peaks left and right are the carboxylate peaks, the oxalate peaks, and they shift properly when you isotopic label, and there is no involvement of the oxygen in the substrate scene. And if you then change the temperature, this is shown here, you see the oxalate peaks happening, occurring always when you have the lower temperatures. However, when you start to temper, to thermally elevate the temperature to a certain point around 500 or so, 550 degrees, then you start to see the disappearance of the oxalate, which can be directly interpreted as the loss of the charge on the gold, thus not being able to activate the CO2 to form the oxalate. So I think we have identified in this case the possibility of showing that the electrons transferred to the gold cluster activate the system, and as the system is activated, it can undergo interesting chemistry at very low temperature induced by the electron transfer. And the oxalate, of course, can, for example, be reacted with ammonia, and you get urea. Very interesting molecules can be made. Now, when I tell this story, people will always say, well, come on, this is a very esoteric story. It's on thin films. And how does that connect to the real world? And the answer is, well, the concept is that obviously if you can charge transfer, or you can provide electrons to charge transfer, the morphology of the particles change, and that morphology then triggers the chemistry. This is, by the way, this is, I forgot to say, this is the change in the gold morphology as we change the temperature, not so important. But can we do this also for not thin films, but for models representing bulk materials as you would have them in a real catalyst? And the answer is, of course, yes, because we have to just change the electron transferability of the substrate. And that's what the semiconductor industry has done over decades by putting dopants in. And so we can just try to put dopants into our thin film, the thick thin film, and see whether we can use dopants that allow you to transfer electrons. And you can, of course, immediately understand what the problem is. You need to have a dopant where the energy that is necessary to release an electron is low enough that you can win by putting the electron on the gold on top. And a system where we have studied this is calcium oxide, and it's basically the same as magnesium oxide, but it was done on calcium oxide in this case, and it was done on a molybdenum substrate. The point is that when you take a thick calcium oxide film on a molybdenum substrate, get the same situation as I've shown you before. three-dimensional gold particle, nothing special. However, if you go to thin films, to thick films that are doped with molybdenum, and you can imagine how we got into this. Artificially, we heated the system too high, molybdenum starts to diffuse in the film, and all of a sudden we saw these funny things, and then immediately thought, oh, we can use that. And of course, you can do that in a controlled way by putting calcium oxide down, then put a little bit molybdenum in and control all this in detail. And the interesting thing is, if you have this dopant in, pancakes occur. All of the particles of pancakes. And you can see here this beautiful moire pattern, which comes about when you have two lattices rotated with respect to each other, allows you to very precisely determine the interatomic distances. It's exactly the one that you expect for gold. And if you want to see how you can also, and I didn't show you that for the thin film, but here you can actually atomically resolve the thin films on the calcium oxide. So we can provide, based on the concept, an idea how we can create real catalysts by doping and control the morphology of these gold particles. And there are groups actually studying this in real catalysis. This brings me to the second example. And the second example is, as I said, directed towards understanding chemical reactions in confined space. And I have to give you a little bit of an introduction to this. First of all, we are not the first ones to study or to try to study chemical reactions in confined space. There is, for example, the Xina Bao group in Dalian in China, who have studied intercalation of molecules underneath graphene sheets on a metal surface. They put particles into single wall nanotubes, for example, or this is the point that I spoke about before, that's zeolites. Or you can put them, you can try to see how you have to alter the molecular shape to bring them into the single wall nanotubes, for example. Bao and his group has also studied reactions, CO oxidation on these graphene sheets, but there the clear identification of the reaction, that the reaction takes place underneath the carbon sheet can be debated. My collaborator Shamil Shaykhutdinov has tried to put CO underneath a silica film, and that's shown here on the right-hand side. And this, of course, will be the topic of what I tell you in a minute. What we can do is we were interested in getting silica films because silica is such an important support material. And when you start to grow silica films, you can actually grow them on various substrates. And we started growing on different metals, palladium, platinum, ruthenium, molybdenum. And it depends very much on the affinity of the metal underneath, whether a silica film grows as a monolayer or a bilayer. And I will explain to you in a minute what a bilayer is. But this sheet shows you directly, this is a lead pattern, which shows you the crystallinity of the system. And this is a lead pattern after some treatment. And you see the crystallinity is gone. You see an amorphous, typical amorphous ring structure. If you look at the SDM images connected to it, and I will explain to you in the next slide, you see clearly a very, very well-ordered structure on the left-hand side for the crystalline material, and a much less structured material on the right-hand side. You will see in a minute in the slides that this is a 6-membered ring here, these little things, and these are different ring sizes, as you will also see in a second. Here is a picture where you can directly see what I mean by the bilayer silica film. This is the monolayer. So there is a silicon atom in the middle, 4 oxygen and a tetrahedron around it. And one of the oxygens is bound to the metal. And that binds this silica film very strongly to the support. For example, in the case of molybdenum, this is the only one that forms because molybdenum has a very high affinity to oxygen. However, if you do the same thing on, say, ruthenium, you can actually grow, you can grow a layer that is a so-called bilayer. So you take that monolayer, flip it over, and bind a second layer on top. And this is fully saturated. So this one has a stoichiometry of SiO 2.5. This has a stoichiometry of SiO2. So this is a clear silicon dioxide. And you can see in the infrared, this blue one is this one. It has no silicon oxygen metal bond as the monolayer has, as you can clearly see in the infrared spectrum. And this silica film is not bound with strong chemical bonds to the substrate, but with very weak dispersive forces. And that gives you the possibility to use the space between the metal and the silica to do something. It gives you also the opportunity to look in these structures in very, very great detail. And Markus Heide in my group has developed a scanning probe where you can take non-contact AFM and STM on the same atom. So you can actually image, in this case, one of these non-crystalline films. You can image them with the non-contact AFM, which gives you the contrast of the silicon atom. And then you can image the same area with the STM, and yet that gives you the oxygen contrast. So by putting the two on top of each other, you have the chemical map of this thing. So in other words, the amorphous structure is built by having SiO4 tetrahedra, not just arranged in hexagons, as in the crystalline thing that I shown you before, but with different ring sizes. And interestingly enough, that proposal, nobody has seen that with atomic resolution before. People have done X-ray imaging and modeling and have suggested that, but this is the first time you see it. And here you see a picture that Bill Zachariasen, a Norwegian immigrant to the United States, published in JACS in 1932. That's the Zachariasen model of the amorphous silica. This is the first time 70 years after, or even more, how many? Yeah, well, 80 years after, that you actually prove Zachariasen completely correct. So I'm showing you this because this gives you an opportunity to characterize your material at a very high and atomic level. And you can see this is, here you see the hexagons on the left of the crystalline structure, and you can see the different ring sizes on the right-hand side. And you can see there is obviously a transition area from the crystalline to the amorphous side. And we are investigating this change in the crystalline to what people call the glass. That is the crystal glass transition at atomic resolution with a very fast scanning STM, which is being developed in the group at present. So we hope eventually we will be able to say, this is the way this happens in detail. We can already count ring sizes and get some idea. And we can actually do a measurement using a microscope that works at the synchrotron, where we can do LEAM experiments on a large area. And you see in the top here, this is a crystalline phase, and this is the amorphous phase. You see the elite images. And if you do this as a function of temperature, then you can actually determine the apparent activation energy change that you need to go from the crystalline to the amorphous phase, and this is shown here. And the value that you get is 4.2 electron volts. Pretty high energy, but it's completely consistent with the so-called stone Wales defect, where 4 6-membered rings turn the middle silicon oxygen silicon bond and form 2 7 and 2 5-membered rings. This is known from graphene, by the way, but you can see it here being involved. And this is a detailed theoretical study that has recently been performed by Marek Sierka in Jena. Now, what has this to do with the confined space again? This is the idea. We have a silica layer on top, and we have a metal underneath, and we can saturate that metal with oxygen. And then we can diffuse hydrogen through the silica pores and make it react to water. And if you do this, you can then again use our microscope where you can do LEAM and also X-beam to study this reaction. And here's a little video where you see the reaction front. The reaction front is showing that the reaction for hydrogen to water is on the right low corner, and as the reaction front moves through the area, you can see how it moves, and you can determine the speed by which it moves. And you can see that the little darker lines are actually step bunches on the single crystal, and there, when you look in detail, the front stops for a little bit. So it's obviously influencing this thing. And this is interesting, because why do you have a reaction front? Well, we first start with oxygen covering the entire surface. And if you have an oxygen, full oxygen layer, hydrogen cannot dissociate on the surface. There is no site for the dissociation. However, in any surface, you have defects. And the defects have lower oxygen concentration. And that's where the hydrogen starts to dissociate. And then from this on, the reaction goes and leads to this propagation of the reaction front. So by analyzing the reaction front, you can see it up here. You can stop it any time. And you have an oxygen-rich area where the oxygen is still on the surface, and an oxygen-poor surface where the hydrogen has reacted away the oxygen. And you can see this with XPS. This is the oxygen silicon, and this is the oxygen that sits on the ruthenium, and the way it is gone when you go from oxygen-poor to oxygen-rich. And so you can identify this. And this then, as you do it by as a function of temperature, allows you to determine, again, an apparent energy. And the interesting point here is that that apparent energy of activation for the creation of water from hydrogen and oxygen is around 26 kilojoules per mole. Now you can also rip this silicon apart off, and you get then the open space reaction. And if you then measure the value, it's about 60 kilojoules per mole. So it's a factor of 2 bigger. By the way, this open space reaction has been looked after by Dietrich Menzel, who is also an author on this paper, 20 years ago. So, and this has been full agreement. So why is it that the apparent energy goes down by a factor of 2? And this is something where chemical engineers come in and they tell you, oh, that's clear. This is diffusion control, because due to the layer, the reaction is controlled by the diffusion, water away and hydrogen, how it comes to the reaction. And that gives you, in general, typically a factor of 2. That's true, but what are the detailed processes involved? And this is something we're after by looking at the elementary steps. And we do this together with Joachim Sauer, Dennis Uzviat, and Tom Mullen, who's the PhD student. They work on the on ab initio DFT calculations to get all the activation energies and so forth out. But then again, we work with a theoretical physicist at the Free University, Mark Schluto, who has developed models, models to look at reaction fronts. He's someone who works typically in the atmospheric region, where they look at models for cloud formation and things like that. So he has mathematical models to do that. And he can show what the key factors are in dissociating the hydrogen, moving it exactly through the reaction front, finding the right space, and bringing that in contact to the DFT calculation. That's something that we are working on at the moment. And I have a very clear feeling that in very short time, we will be able to really look at the details of understanding this confined reaction again at the atomic level. With this, I'm at the end of my little presentation. I showed you 2 things: negatively charged supported gold clusters to activate CO2, at the oxide metal interface, and that's where the electrons sit, because I forgot to mention that they sit at the rim. Why? Because they want to get away from each other, and that's where the CO2 picks it up. And secondly, I showed you that surface science may be an interesting access tool to get information on spatiotemporal phenomena in confined space. Here is the group that used to be my group. This is no longer my group. My group has shrunk from many people to only 3 or 4, but that's fine. But I would like to give them credit, because I'm only the clown presenting it. They should get all the credit because they have done all the hard work. We have the pleasure of also interacting with what we call post-profs. That is, people who are retired, who are still interested in science, and they work with us. And we have a very strong collaboration with theory groups mentioned here. And of course, we have also very strong connection to the Humboldt Foundation, who has funded a large number of Humboldt awardees and Humboldt fellows through the years. And this is the last meeting of our department at Ringberg that we had every year over the last 23 years. And you wonder why people hold this little thing in the hand. That has to do with the fact that Günther Rupprechter, who is shown here, who is a professor now in Vienna, brought a Mozart sphere with him. And the Viennese think that their Mozart spheres are much better than the original ones from Salzburg, because you can build up, they are really spheres, and you can build up little two-dimensional models of metal particles made out of chocolate. So these people are the ones who should get all the credit. And with that, I thank you very much for your attention.
Thank you so much, Dr. Freund, for that amazing lecture. Thank you. We have several questions for you that I'll read to you right now. Firstly, generally, what is the method to make nanoparticles on such single crystal or thin films? You mentioned physical vapor deposition, but would precipitation also work? And how can you control the dispersion and distribution?
Right, that's a very important point. I mean, precipitation would in principle work, but the point is, usually when you use precipitation, you have a liquid that you use, and that of course makes the system much more complicated. Mm-hmm. You have to remove the liquid and make sure that you still contain the atomic structure of the system, and people have tried, and that's often not the case. So it's much more tricky. But with precipitation, of course, it's much easier to control the dispersion. But in our case, we control it by very carefully controlling the temperature and the flux. And it needs a while. You cannot just say, oh, we do this and we'll get this dispersion. But you can figure it out if you really do it very carefully.
Great, thank you. Could you comment on how to create a defect in your system or surface?
Yeah, the good point. I didn't mention that because too much to go into the details. But one way of creating defects is either you heat the system up very high, or you use electrons. You can shoot electron beam onto the surface, and that removes, if you do it carefully, you can actually control the energy of the electrons, and that allows you to remove individual oxygen atoms in a very low concentration, as you had seen in the SDM. It was actually indeed done by electron bombardment.
Awesome. Regarding the gold particles on your magnesium oxide, I know magic number theory can predict cluster stability and size, and charge transfer between substrate and cluster can also be considered. With that in mind, were other gold cluster sizes observed on the surface? Because magic number theory would predict there would have been few.
Yeah, well, in this case, we don't really have only magic numbers. I mean, the gold 20 cluster in the gas phase was taken by Uzi and Gianfranco as a model system. That was actually done before we did the experiment. And for us, it was not so important to control the number of gold atoms in the particle, but rather to control the number of electrons being transferred. For that, we need to know, in the specific case we created, how many gold atoms are in the particle, but it doesn't have to be a magic number. And there are not only magic number of particles that are created. Mm-hmm. So because, you know, the magic number game comes about because you create a certain number of gold atoms. You have an orbital diagram you can fill in, and you know how many electrons you have to fill in to really close it up. Mm-hmm. And in our case, the substrate basically provides any source, any number of electrons that is needed to stabilize the system.
Right. Thank you. Have you considered changing the cluster morphology by alloying the clusters? Gold and vanadium have shown some interesting characteristics and change morphology and local bonding environment depending on size.
Okay, yes. I mean, this is something that people are studying now, trying to alloy these particles and also to change the material components, right? I mean, you can clearly imagine that as I tried to convey to you with the dopants, it depends very much on what you use as a dopant. And so in the case of the thin film, it is important what kind of an oxide you have, what kind of a metal you put on top, and what kind of a metal you have underneath. Because the critical energy is how much does it cost to remove an electron from this buried oxide metal interface, and how much do you gain by putting it through the electron affinity of the cluster on top. And that is, of course, material dependent. And the electron affinity of the cluster, of course, depends on its alloying character. I mean, if you alloy it with palladium, so the electron affinity of parts of the gold cluster, but also sort of average changes because of the alloying. And then you have to have the right metal substrate combination to allow it to happen. But I think there is no limitation to think of ways to do that. But we haven't, for us, with having the concept and understanding what the concept is, was the point we wanted to make. And I know there are groups working on it and trying to figure out the details of behind the question that you were reading to me.
Thank you. Could you comment on how to do kinetic studies for your atomic scale modeling? Specifically kinetic studies?
Oh, you mean theoretical modeling of the kinetics?
Mm-hmm. Yes, exactly.
Okay, well, for the reactive modeling of the kinetics, what you need is of course, the energies of the material involved, and you need calculations of the transition state. And once you have the transition state, then you can basically determine the activation energies, and you can solve the kinetics, right? But you can also do Monte Carlo simulations to understand how atoms and molecules move on the surface and so forth. People can do this. And as I said, Tom Mullen is the student. He's calculating all these transition states, for example. What Mark Schluto does is he doesn't do an atomic level calculation. He uses mathematical models to use the derived kinetic equations that I briefly showed, to put them in and understand, given what the kinetical constants are from the calculations, how that changes the way the reaction front behaves. And if you put all this together, then you can see, what do I need to do to get a situation that fits my experimental observations? And then you can perhaps go to conclusions. And that's what we're trying to do at the moment.
That makes sense. Thank you. Thank you very much for the nice presentation. One quick question about the metal oxide layer supporting the metal clusters. I saw mainly used magnesium oxide and calcium oxide, these low density or light materials. Have you ever used any dense metal oxides such as cerium oxide, zirconium oxides as support? Are they going to bring any difficulty in STM characterization for the support metal clusters?
Yes, we have done it many, many times, and you can read the literature. You can find my set of papers on my website, and there is also work on cerium dioxide quite a lot. We've worked on it, and we've done iron oxide, chromium oxide, molybdenum oxide. I mean, what you name it. I mean, we haven't done every oxide, but you can in principle do it on every oxide. One oxide where it's very difficult to grow very well and bulk resembling thin films is titania, interestingly enough. But there you have a single crystal, and the single crystal with niobium dopant can be made conductive, and then you can do these experiments on the single crystal.
Right. Thank you. And last question, can you comment on the change of work function at the interface when we form multi-layers on substrates?
Of course. We have measured this, and you saw it in one. Can I still go through my slides?
Yeah, we see
okay. Now you can see here in this part. You can see the changing work function, because in principle this change when you have the oxygen on and the oxygen off, this difference in this drop here gives you the work function difference.
I see.
And so you can do that in for any of those cases. It's also for different materials, of course. But this is the way, for example, to do this. But you can, of course, do this also with a vibrating capacitor and things like that. But yes, of course, yes, that can be done.
Thank you. Thank you so much. So I'll just put my concluding slide up here. Let's see. There we go. Thank you so much, Dr. Freund, for all your time, for sharing your knowledge. I really appreciate it. Yes, thank you.
My pleasure, and I thank you very much for inviting me to give the talk. It is a new way of giving talks for me, but I like it a lot. And thank you very much to all participants of the seminar, and thank you for your time and effort to setting it up.